So this is more about the causal assumptions that we generally make for some of the interpretations or analysis that we do under the causal inference framework. And for that, I'm just going to use this book as a reference, particularly the chapter 3 of this book is going to be the reference. So before I talk about anything else, let me just be a bit clear about what are the notations that I'm going to use here. So as usual, this is my exposure. This is my outcome. This is a confounder variable. This is a proxy variable to that confounder. This is a variable that is associated with the exposure. So you can kind of think of it as a variable that determines subjects getting the treatment. This is something that is the risk factor. This R is the risk factor for your outcome. This is the effect of outcome. This is the mediator, and this is a noise variable that does not have anything to do with any variables in this particular DAG. Randomized clinical trials are the gold standard for trying to get the treatment effect estimate. And the idea is that if you are doing randomization, when you have enough sample size, then confounding is not really an issue. And this is a larger statement than most people think. Confounding is not really an issue does not mean that only the variables that you have observed. It also includes the variable that you did not even observe or did not even measure. Randomizing is a very powerful tool that works not only for the observed, but also for the unobserved. Everything that is out there, by the process of randomization, you can eliminate confounding by any type of observations. Generally speaking, there are exceptions, but this is generally speaking. So the question is how to estimate unbiased treatment effect from a randomized clinical trial. So the question is saying only one criteria, unbiased treatment effect, right? So there was one student who said that if you just feed a regression where y is the outcome and indicator of the group determined by randomization is the variable that you need to adjust to get the unbiased treatment effect. So when you are doing your randomization, you are essentially trying to determine who goes into the treated group and who goes in the control group, right? And this indicator is basically saying that who goes into the treated group and who goes into the control group. So in a perfect world, if there was no issue with people deviating from protocol or anything like that, whoever was assigned to the treated group would be getting the treatment. Whoever was assigned to the control group would be getting the control. But in real world, sometimes that may break down. Some people who are assigned to the treatment group, they may not take the treatment. They may discontinue the treatment and all of that. If there was no other issue, I'm not being dramatic. I'm just trying to figure out what is it that gives me that unbiased treatment effect. Then this would be the correct answer, right? And obviously, by extension, this is again the correct answer because in a perfect world, this indicator and this A should not be different, right? All right. I'm surprised nobody chose this one. Okay, so what is going on here? So here I have a Y and I have A and I am adjusting for C. But by the process of randomization, what is happening is that link between that C to A, that link is broken. So I do not necessarily need to adjust for C anymore. But let's say I'm still curious. I adjust. What is going to be the impact for that? Okay, so in the process of randomization, what is happening is that the C variable that you have, it has one link to the exposure and one link to the outcome. By the process of randomization, you are removing the link from C to your exposure, but still C to Y link is still there, right? So that confounder now becomes the risk factor for the outcome, right? So this will not really, like if I am using this after randomization, mind this is happening after randomization when you have already broken the link. This has turned into a risk factor for the outcome. And when you are adjusting for this A and C in this analysis, then what is happening is that your bias level will not move because there was no confounding to begin with. But since you have included a risk factor for the outcome, your standard error for the treatment effect will be smaller now. You will have a more precise confidence interval. But if you go back to the original question, does that give you an unbiased estimate? Yes, it does. There is no problem with that if the randomization was perfect. What about this one? You are including A, C, and risk factor for the outcome. Basically the same answer. Basically, this will give you the most precise confidence interval when you are including your confounders, where the link between the confounder and exposure is already broken by randomization. So this has turned into the risk factor for the outcome. And then you are including the pure risk factor for the outcomes. That has nothing to do with your exposure. So this analysis will give you the best estimate in terms of the confidence interval, the preciseness. What is going to happen with the bias? So this is again a correct answer, right? What is going to happen here? When you are including something that is a determinant of the treatment assignment, right? So the problem with this type of determinants of treatment assignment is that sometimes you do not know whether this is a instrumental variable or not, right? And if you are including an instrumental variable in your analysis, particularly when you are doing propensity score analysis, then not only you will get a larger confidence interval, the precision is going to be worse, but also it can induce some bias in your analysis if you are including strong predictors of your treatment assignment. So this is something that we are not going to use. How about this? Again, unbiased, but precise, but not as precise as this one. What about this? I'm only including something that is inducing some bias maybe. So out of all of these, only the ones where I have the strong predictors of the treatment assignment, I'm not going to include that. Other than that, if you are asked about a plan where you are supposed to list many different strategy, then you can list this one, you can list this one, you can even list this one, right? So those are the options. So this is the one that is ideal in a randomized clinical trial. Many people prefer not to adjust for anything, but if getting a precise result is also a priority for you on top of getting unbiased result, this is going to be another answer for you. So think about in a randomized experiment, when you are randomizing, your objective is to randomize to the exposed group or the unexposed group. That is the sole objective of a randomization in a randomized experiment, right? And you try to decide by coin tossing whether a person is going to the treated group or untreated group, right? In a randomized clinical trial. So this A variable that you are seeing, some people were exposed and some people were not exposed. Those were basically determined by this randomization in a randomized clinical trial. So in a perfect world, if there was no protocol violation, then this indicator and this A variable should be exactly the same. So this is my C, the confounder, and this is my exposure variable, and this is the outcome variable. And by the process of randomization, what is happening is that previously there was a backdoor path open, right? By the process of randomization, I am completely eliminating this particular arrow. So that is what that randomization is doing. But still, this arrow has nothing to do with randomization because we were randomizing with respect to who goes to the exposed group and who goes to the unexposed group. So when you remove this arrow, there is no backdoor path anymore. This becomes just like this one. The C variable just becomes another R. All right. So now assume that you still have a large study, but it's just that there was no randomization in the assignment of the treated group versus the untreated group. Then one of the ways the causal inference people think about getting or recovering the true treatment effect is to think of their or maybe comparing their observation study with a randomized clinical trial and try to see what is different in this observation study, and they try to rectify that those differences. Basically what that means is that they try to identify the conditions under which this randomized clinical trial work, and they try to see whether those same conditions apply to the observational data analysis that you are doing, right? So by breaking that link between C and A, what is it that you are achieving in a randomized clinical trial that you are not achieving in a observational study? One quick example is this RHC dataset that you have seen during your propensity score um, class. And this is just part of the table where this is after randomization, this was no RHC and this was RHC. And you see this is age range, sex, race, and there was a lot of other variables. I did not include them. But see, there was 3,000, more than 3,000 people here, more than 2,000 people here. Still percentage wise, you will see this is 25%, this is 25%, this is 14%, this is 8%, this is 24%, 23%. The percentages look very similar. And you have done nothing other than this randomization, and that is bringing all of this. This is like working like a magic. Similarly, for the sex, you can see 54%, 59%, 46%, 41%. Obviously, it is not exactly 41% and 41%. It is not, but it is close enough so that you get some assurances that both of the groups are balanced. Same with the race, 78, 78, 17, 15, 5, 7, right? So this is the magic of randomization. It brings balance to both of the group so that the link between this C and A is completely broken. And only thing that is left is this R and C variables maybe, and then simply adjust for those because those are something that are going to give you high precision when you are adjusting for that in the analysis. Let me talk about what is going on with the other stuff. What do you think happens when you adjust for this M? This is breaking down your effect. So remember the Baron-Kenny approach, especially the approach 1. This will break down the total effect into the direct and indirect effect. What will happen if you adjust for this N? The variance will be higher for the treatment effect. What happens if you adjust for this P variable, if you are not adjusting for this C variable? Exactly. If you have a very good proxy that can ultimately replace this C variable, then whatever you are saying that it will have no bias and reduce precision and all of those will happen. But if this is a kind of not so strong proxy, then you do not know in which direction the bias is going to go. Is it going to be in the plus direction or minus direction? Obviously, we expect that if you are including a good proxy, we will reduce the bias. But depending on the strength of the proxy, uh, that bias might not be zero, right? So obviously, adjusting for proxy is something that reduces our confounding or bias, but there is no guarantee that it will be zero, and there is no guarantee that it will be in the plus direction or in the minus direction. So generally speaking, if you have two variables, say for example, the C variable and this P variable, if you simply check their correlation, that will give you a very good idea about how good proxy are they. If they are not even agreeing with each other, right, then probably it's not a very good proxy. What is going to happen if you are adjusting for this E variable in your analysis? It will induce bias. Yes, that is true. Your analysis will go in the wrong direction if you are simply adjusting this V variable in your analysis. But there are other analysis like instrumental variable analysis and all of these that can adequately adjust for that V variable, but not your regular regression. Especially if you are doing some sort of conditional randomization, that within this group you are doing this randomization, then probably this V variable could be useful. But in a completely randomized experiment, this V variable will not have anything to do with it because all of the links from other variable to this A will be broken by the process of randomization. All right. So what are the things that are available when we do randomization that are not available when you do observational study? And those conditions are laid out in the literature, and they are usually known as the identifiability condition. Basically, what it says is that if you have a randomized clinical trial, then conditioning on this L variable is not really necessary. Say, for example, the stratified randomized design or something like that, then this conditional probability will be necessary. Say, for example, if you are doing one randomization for the male group, another randomization for the female group, then you will need this conditional randomization variable. You can think of your observational study as an extended version of that conditional randomization, where you are basically doing randomization with respect to many covariates. And I'm going to explain that part a bit later in the next few slides. And this will require you to have access to all of these L variables. Because if you do not have access to this L variable, you cannot really condition properly to get the proper probability, properly get estimate of this conditional probability. So this assumption is usually known as the no unmeasured confounding or exchangeability assumption, where you are basically saying that if you control for L, say for example, in my example, if I was randomizing with respect to male first and then I was randomizing with respect to female first, then within the male group, my potential outcome and A would be independent, right? And this is different than saying Y is independent than A, because if there is a treatment effect, Y will never be independent of A. But this is not treatment effect. This is the notation for the potential outcome. That if you received treatment, Y in parenthesis A equal to 1 would be your outcome. If you received control, then Y in parenthesis A equal to 0 would be your potential outcome. And that part I will be explaining a bit later in the next few slides as well. The next definition is more about whether you have a well-defined treatment or not. And that has more to do with the potential outcome notation as well, and I will explain that. And the last point that we need in a randomized clinical trial is that within each group, if you're doing a conditional randomization, you need the probability of each group to be greater than 0. Otherwise, this will not really work in terms of your comparability. And this is known as positivity. All right, let us resume with our discussion. Uh, so let us work with a particular example where, say, for example, John is a person, and this is a similar example that I have given during your propensity score lecture, where John is a person who takes some cholesterol medication such as rosuvastatin, and they are under different treatment. So what this exchangeability is meaning is that if their potential outcomes were exactly the same under same treatment status, then we are saying that this John and Jim are exchangeable. And note that there is no condition attached to it. So it's just that their potential outcome are exactly the same. So there is no particular condition of what were their age or what were their other demographic characteristic or anything like that. So here is the same example where John and Jim has exactly the same potential outcomes under the same treatments. So this is the potential outcome under the rosuvastatin, and this is the potential outcome when they do not take the rosuvastatin. But when we have incorporated Kate and Hilda in our analysis, we have seen that their potential outcome levels are different compared to John and Jim. And the only difference in their characteristic were that these first two were male and the last two were the female. So in that case, you will see even for Kate and Hilda, your potential outcomes are exactly the same under the same treatment status. So in that scenario, you would say the potential outcomes, notice here I'm not saying observed outcome, I'm saying potential outcomes are independent of the treatment assignment. No matter whether you give them, assign them in the treated group or not in the control group, their outcomes will be the same if we simply adjust for the sex variable. So this would be an example of conditional exchangeability when we are conditioning on this sex variable. This is the slide where you link between your potential outcome and the unmeasured confounding assumption. Is that if you do not observe this sex variable, if you do not measure this sex variable in your data collection process, if you just have this y0 and y1, right? Say, for example, you are only observing one part of the data, that's fine. But if you do not have this sex variable, then you cannot really adjust for that sex variable in the analysis. And your whole analysis will be biased because you have not been able to adjust for this one variable that was necessary to make sure that they are conditionally independent, right? So if you do not measure this sex variable, whatever fancy analysis you do, it is of no use. It will never be equal to the exchangeability assumption if you are not adjusting for this particular variable. And you can again expand that to include even more variable. Say, for example, in here, John and Jim are very similar. Kate and Hilda are very similar, but Joseph and Jack are, even though they are male, they are very different than John and Jim. And the only differing factor was the age. These two gentlemen were 20 years of age, and these two gentlemen were 90 years of age, right? Same for the Kate and Hilda and Anna and Melissa. They're here the potential outcomes are the same. Anna Melissa's potential outcomes are the same, but Kate and Anna are not same because they have different age group, right? So in this case, if you do not measure sex or age, either of these variable, if you just do not measure age, say for example, this conditional exchangeability assumption, like you can always have the assumption, but you will not have the ability to address that when you are doing the analysis. So that is the link between the exchangeability and the no unmeasured confounding. If you have a confounder that is unmeasured, you will not have any ability to adjust for them in your analysis. So in this type of analysis, in a realistic data, when you are not really dealing with potential outcome, you are dealing with observed data. What happens is that you only observe one of these two, right? You do not have any time machine to go back to give them treatment or no treatment. You only observe one. So in this case, even in this case, if you know the exact list of the variables that are necessary to adjust, you can still recover the treatment effect if you are simply adjusting for those variables in a, say for example, regression could be one way to adjust for it, propensity score analysis could be another way, stratification could be another way, restriction could be another way. There are many different ways by which you can estimate the treatment effect by conditioning. And the conditioning come from many different analytic approaches. There is no restriction about that, but you have to have access to this age and sex variable in this particular example. Even if you do not observe both of these, just by having access to this, you can still get, if you obviously not only with these 8 subjects, obviously you need reasonable amount of subjects, then from this regression you can still get a reasonable treatment effect. Remember what was the magical power of randomization? You do not care whether you have measured age or sex. Randomization will make it balanced. So generally, you can view observational study as an extension of randomized clinical trial when you have these more and more conditions. You can simply do a matching that will immediately give you a ATT. And if you want ATE, you can do a weighting approach that will immediately give you a ATE if you are using the ATE weights. Sometimes even if you are doing randomization, sometimes your randomization is not successful. Maybe because your sample size was not good enough or something like that. Sometimes your randomization is broken. So it is a very good idea. And that is why you will always see that the clinical trial papers will always start with a table 1. And what is this table 1? Always checking whether the groups are balanced or not. And if they're not balanced, one of the suggestion is to adjust for the variables that you do not think are balanced. All right. So forget about the data generating process. Now think about, you do not know about the data generating process. So in the situation you have this only this observed data, and you have some variables that you think are going to be those conditional variables, right? And then we analyze based on the assumption that we have the sex variable and age variable um, that are confounders. But how do you know that these are the two variables when you do not know the data generating process? How do you know that these two variables are the variables that you need to adjust? There could be some other variable like income variable, say for example, that could be also something that was contributing to the difference in the potential outcomes. How do you know? From an empirical point of view, when you have access to just this observed data and some covariates, from the data itself, there is not much reliable way to get a sense of what else we can add to adjust this. So that brings me to this quiz now. All right, so the quiz that you are answering right now, the answer to this is $1,000,000 question. So nobody really knows what is going to work. You are kind of in a fishing expedition, right? Let me explain why that is the case. So most are answering subject area knowledge. This would be obviously true for a topic where you have numerous studies about the exposure and the outcome, and everything there is to know about that topic, people already know. If that is the case, then probably um, this subject area knowledge would be somewhat adequate to adjust for the conditions or the variables that are necessary to adjust. But most of the research that you do, say for example, even consider the final project that you are doing, do you think that subject area or the literature already knows what are the things you need to adjust? Probably not. So just relying on subject area expertise is probably not going to be the best strategy. How about some of the empirical selection strategy, like when you are selecting covariates where A is the outcome, or when you are selecting the covariates where Y is the outcome? Problem is, when you are selecting the covariates using where A is the outcome, you might attract instrumental variables in your analysis. When you are trying to use Y as an outcome, there is some evidence that might lead to you a better covariate list, not necessarily only the confounders, but also some of the risk factor for the outcomes. But from our previous slide, we already know that not only the confounders, but risk factor for the outcomes are also helpful when you are adjusting for them in the analysis, right? So some sort of combination of the causal criteria as well as the empirical criteria would be something that is probably going to give you a practical solution to this complex problem. And that is why you will see in the literature people uses all of these approaches. Why? Because people do not know. I do not know. You do not know. We are just all analyzing the data. We are all analyzing the literature, and we are just trying to get a better sense of what is going on. When you are doing the randomization, you do not necessarily need to know what is this u variable you have, because you do not need to adjust for anything. You just do a y versus a type of analysis and you are done, right? So when you are moving away from randomization, then we need to exactly know what are the variables that is impacting the potential outcomes, right? And that is the main problem of observational data analysis, that we do not know the whole list, and we are scrambling to find out what is the whole list. Unless we have the whole list, we probably might never know what is the true treatment effect. But we can come up to a reasonable solution that maybe we do not need all of the variables. How so? Say for example, this sex and age variables are probably most determinant of the data generating process, but that income variable has maybe some impact, but not so much that we absolutely need to adjust for it to get the exact unbiased estimate. It can give you a closed unbiased estimate, close to unbiased estimate, if you are not even adjusting the income variable that is not really highly determining the data generating process. So you can come up to a reasonable or pragmatic solution that the variables that are most determining the data generating process, you are adjusting for those. Rest of the variables, yes, we have some of those, but we do not have access to those. So we live with the estimate that we get. In the epidemiological literature, especially in the good journals, when you say that I have done the analysis and I came up with a unbiased estimate, they will immediately say no. Change your wording to say you have reduced your confounding. But coming up to an unbiased estimate is something very divine. Last piece is about positivity. And this positivity is assumption. What it says is that when you are talking about this conditional exchangeability, you need to make sure that you have positive probability for all of the different conditions that you are outlining. And it cannot be 0. It cannot be 1 either, because if it is 1, if A equal to 1 and sex equal male is equal to 1, then A equal to 1, sex equals female is going to 0. So you cannot allow any one group to be 100% certain, or never can happen. It always have to have some sort of, even if it is low, it has to have some sort of probability. Otherwise, you cannot really estimate or compare what you are trying to compare. So we are trying to estimate that probability of A given L, where you have measured L, right? And in that scenario, what is your answer? Most are correct, actually. So the answer is sometimes. And let me try to explain that why that is the case. So there are two different types of positivity violation that can go on. One type of positivity violation is the structural violation. That means that there is a certain group who can never have the positive probability, no matter how many data you gather, right? And there are some other positivity violation that are known as random positivity violation. That means that in the data generating process, there are some people who falls under that category, but due to the small amount of sample size you have collected, maybe there was no person who got selected in that particular category. So that means if you are trying to empirically check whether there was a non-zero probability for any particular group, sometime you might get wrong answer, right? And sometime you might be able to get the right answer, because for that group, it will always be 0. So the answer to the previous question that I have asked is sometimes, because sometimes you can do it, but sometimes due to the data limitations, you might not be able to figure out whether that was a true positivity problem or just a random problem. Also, many have chosen the last one, last option, where the idea is that when you are not doing randomization, you are not really collecting all of the information that that can be collected and controlled. That is not essentially necessary, because, say, for example, you have this positive probability and you can check that there was some people in your cohort who had black eyes, brown eyes, but there were no people in your group who had blue eyes. But if eye color has nothing to do with your outcome and exposure, you do not really need to adjust for that L variable. So whether that variable is positive or not, whether that probability is positive or not, that is kind of irrelevant. So you all only need to worry about those L that are relevant for your unmeasured confounding assumption. Everything else, you do not have to worry too much about that. All right. Do you think there is a positivity problem in this particular data? Assuming this is the whole data in the study. So what is happening here is that within these, you can compare the results to get your treatment effect. Within these, you can compare the result to get your treatment effect. But there is no person here to compare, or no measurement here to compare your effects to get the treatment effect. And same for the last person as well, for Melissa. So for this scenario, when you cannot get a comparable subject on the other counterfactual, so that would form a scenario where you cannot really have positive probability for that age equal to 90 group. So say, for example, if L is equal to 20 and 90 was in your group, and for some 20, you can compare, and for some 90, you cannot compare, that would create a positivity problem. All right, so The last assumption that I'm going to describe is the causal consistency, and this is a actually this causal consistency has many definitions, but I'm going to stick with the easiest definition, because if I want to explain the other definitions, that will probably confuse you a bit more. But let me give you that definition anyway, uh, because this is the act observed y, and this is the uh, potential outcome under treatment. And what this assumption is saying, that both should be equal. What does that really mean? So to understand that, let me think about a very specific dose of rosuvastatin. Say, for example, if I'm talking about rosuvastatin 5 milligram, and I'm saying that rosuvastatin 5 milligram is my doses. And one person who took that certain doses, his observed value is 200. But if someone else took a 10 milligram and his observed value is 150, that is not equal to what we are saying, right? So the main idea is that you need to be very careful about what is your level of doses in your exposure. Otherwise, whatever potential outcome you are coming up with, it can be associated with something else that you did not really observe. To make it even simpler, um, you need to be very specific about what is it that is your exposure. If you have multiple version of your exposure, say for example, in this case, uh, John is someone who figured out that buying 5 milligram costs him more. But if he buys 10 milligram and then there is a pill cutter. Do you know what is a pill cutter? It can cut your pill. But if you cut your pill, if you are not using some sort of industrial device, it may be sometime cutting to 4.5 or 5.5 milligram. It is not exactly 5 milligram, right? Do you think that is sufficiently well defined? Is it meaningfully different, or is it somewhat realistic to assume that everyone will exactly take 5 milligram all the time? Right? So that is the real question here. So obviously we want to be very specific about our treatment version, but if there is some variation that is kind of ignorable, that is okay. That's what I'm saying here. So this assumption is also known as the treatment variation irrelevance. That means there might be some variation, but the treatment effect will essentially be the same. So in that case, we will have causal consistency. But if we have one person is taking 5 milligram, another person is taking 50 milligram, then the treatment effect that you are getting is some sort of mix that will make no sense. That causal effect of what, that would be the question then. In real life, say for example, I work with a lot of multiple sclerosis studies where they combine all of the beta interferon prescriptions or preparations, where beta interferon has many different preparations. They come from many different companies. They use many different formulas to generate those beta interferons. Say for example, for beta interferon 1A, they have two different versions, and this beta interferon 1B that comes from a different company with a different preparation. So when we are doing the analysis using any beta interferon, usually for getting enough sample size, we usually combine all of the beta interferon into one group, one therapeutic group. And we say that anybody taking Rebif, Avonix, or betaferon, they are essentially taking the beta interferon. And we just get the treatment effect for beta interferon as a whole. But if someone can prove that this Rebif and Avonix has different effects, then that assumption would not be valid. So that is what we need to have when we are talking about causal consistency. And remember, this causal consistency is different than the statistical consistency definition. That is this entirely different thing. So this is the question for you now. After you know this, All right, I hope everyone got a chance to respond to this question. So this is true that if you had a very specific uh, treatment, very well-defined treatment, that would be the best. But generally speaking, in practice, that is not generally possible. If you are trying to have every person in your sample with BMI equal to 25.7, you will probably end up with only few sample size, few people in your sample, right? So you have to allow some variation that is following the following some sort of pragmatic definition. So you may think that this is a well-defined study. This BMI overweight, whatever is the definition, 25 to 30, is a practical definition, right? But think again, because and I'm deviating from the majority in this example, because if a person was overweight for 1 month, or if a person was overweight for 20 years, that makes a lot of difference in terms of the treatment effect, right? So when I'm just saying that overweight is my treatment, what does that really mean for how long that person was overweight? So that is something that is also relevant when you are trying to determine the causal effect. Should not that make you wonder that when you are doing your analysis using cross-sectional study, you have no idea for how long that person was diseased for with a certain disease? Or so, I mean, when you are trying to be a bit overconfident about your result, try to think that there is always some issue that you probably have forgotten. And that is why it is very important to take into account of the reviewer suggestions. All right, so that brings me to the assumptions related to the mediation analysis. So all of the three assumptions we just saw, how they're related to the mediation analysis. And the general way to think about this is that when you are thinking of mediation analysis, this mediator, if you think of this mediator as an extra exposure variable, that actually helps you think about these assumptions a bit more carefully. Say, for example, for mediation analysis, when you are defining your no unmeasured confounding, you are not only thinking about A, but also thinking about your mediator when you are thinking about the potential outcome. Same as when you are thinking about the positivity, you are also thinking about your mediator. And for causal consistency, you also have to extend the same for your mediator. Your mediator must not have multiple versions. Otherwise, the interpretation that you get are not going to be valid. Obviously, there are some other additional assumptions such as no interaction. And this model specification is also a general assumption for not only the mediation analysis, but also the total effect estimate.